Chapter 14 was called Measuring Toxins. Once we were introduced to toxins and chemical equations in Chapter 13, we looked at going a little bit deeper. And really what we focused on initially here was LD50 as a means to show us some information about toxins and what we could do with that information. So we started with LD50. But initially what I showed you guys was a process called dimensional analysis, and that was a simple way for us to set up a conversion. So it was a process to convert from one unit to another. It was especially useful if the conversion was going to be multiple steps. It was a little weird at first. We were wondering why we were doing this and why we were setting it up like this. A lot of us, had other ways that we can solve it using a proportion. But we found that it was very useful when, not only for LD50, but when we got into mole conversions. And again, if the step of the conversion was 3 steps, 4 steps, 5 steps, it was a nice, easy, systematic way to set up the conversion. So really the first piece of content that we looked at here was LD50. And we want to recall that LD50 is the amount of a substance that will kill approximately 50% of a test population. We looked at that big table in the beginning of the chapter, and we saw that these are tested usually on different animals. The LD50 depends on how it's introduced to the body, whether it's orally or intravenous. The most important takeaway with it was that everything is toxic, right? The toxicity of a substance just depends on the dosage. How toxic something is depends on how much of it one is ingesting. Some things are toxic at really high doses, and some things are really low doses that make them toxic. But everything has a toxic limit, and everything has an LD50. The relationships that you should be familiar with are that the higher the LD50, the less toxic it is, because that means the more of the substance you can ingest before you die. And the lower the LD50 means the more toxic it is, because the less of the substance you can ingest before you die. I gave you some sample LD50 values here, but we dealt with a larger table during this unit. But some of the problems we looked at, let's say that we had a 150-pound person, and you wanted to figure out how much of a substance was toxic for them. So let's look at something like ricin. The LD50 for ricin is 30. Remember, the units here are milligrams per kilogram. So it's 30 milligrams of ricin for every kilogram of body weight of the person for it to be lethal. So it depends on the body weight. The more you weigh, the more of a substance you can handle. But this is in milligrams per kilogram of body weight, and we have pounds here. So we use the conversion that 1 kilogram is equal to 2.2 pounds. And that will help convert the body mass from pounds to kilograms. And once we have kilograms, then we can use the LD50, which says 30 milligrams of ricin is toxic for every kilogram of body mass. If we do the math, it's 150 times 30 divided by 2.2, and you get approximately 2,045 milligrams of ricin. We then looked at how we can count the number of objects we have in a sample if we can't see them, because we can't see atoms. So how do I know how many atoms I have in a sample? We did the activity where I gave you a brown bag filled with a certain number of an object. You didn't know how many there were, but your objective was to figure out exactly or about how many objects there were. And the way that we could do this is mass the entire sample, right? So let's say the entire sample of these confetti sprinkles is about 200 grams total. And let's say, because I also gave you a small sample of the item, so let's say I gave you 10 sprinkles, and the mass of 10 sprinkles is equal to 2 grams. Instead of massing just one, we talked about why it would be better to mass more than just one of the object, because they're a little bit different from each other. They should be hypothetically the same, but it's better to mass a collective sample and take an average to make sure that you don't get one sprinkle that was larger or one sprinkle that was smaller. So if we have 2 grams for 10 sprinkles, that means that each sprinkle is equal to about 0.2 grams, right? If we divide that, one sprinkle, about 0.2 grams. So if we have all of these sprinkles as 200 grams, and I know that one sprinkle is 0.2, we can use dimensional analysis to say one sprinkle is 0.2 grams. Our grams will cancel. We'll be left with sprinkles. And this tells me that I have about 1,000 sprinkles in this sample. We related this idea to atoms, but also other objects. In the example I gave you here, I know we used examples in class like sesame seeds and sunflower seeds, but even if you consider baseballs and tennis balls, if you have the same number of each, because each of you guys had the same number of objects in your bag, but the masses were different because each individual item is different. 1 dozen baseballs means you have 12, and 1 dozen tennis balls means you have 12 in terms of quantity. But each one has a different mass. So of course, 1 dozen baseballs is going to have a different mass than 1 dozen tennis balls. This led us to the idea of the mole, right? The mole is a quantifying unit or a counting unit that helps us group atoms or molecules or units, particles, right? Essentially, remember that the term particle could mean either atom, molecule, unit, ion. It just depends on what substance we're talking about. The mole itself, just like a dozen represents 12 things, the mole just represents a really large number of things. The specific number that represents a mole is Avogadro's number. It's 6.02 times 10 to the 23rd. And this is how many items are in 1 mole. Now we can use 1 mole to represent any object, but we use it in chemistry because in a relatively small sample of matter, there's a bunch of particles. That's why the mole is representing such a large number. So again, 1 mole is 6.02 times 10 to the 23rd, or 602 sextillion of something. And in chemistry, that's something is what we're really concerned with, are particles. We looked at molar mass. Molar mass was the mass in grams of 1 mole of a specific substance, and we calculated the molar mass by looking at the periodic table and taking the mass of each atom from the periodic table. So I gave you some examples of how we calculated here. For water, we have 2 hydrogens and then 1 oxygen. Each hydrogen has a mass of approximately 1, and each oxygen has a mass of approximately 16. Now we said, depends on the scale for what our units are going to be. If I'm calculating the mass of 1 molecule of water, then I'm looking at 2 atoms of hydrogen, which would be 1 AMU each, and an atom of oxygen, which is 16 AMU. AMU are the smaller units, atomic mass units, that we use to represent the mass of individual atoms. But if I'm calculating the mass of 1 mole of water, not 1 molecule, but 6.02 times 10 to the 23rd molecules, then my unit is grams. So each mole of hydrogen is 1 gram, and each mole of oxygen is 16 grams. And when I add up or total all of the moles of the elements in that substance for water, we get 18 grams per mole, meaning in 1 mole of water in 602 sextillion water molecules, the mass of that many molecules will be 18. You could practice calculating the molar mass of these 2 other substances here if you want to cover up the work just to make sure you get an answer that's close. You may do that. The picture to the left here is just showing you what a mole looks like for each of the substances in the picture. Again, emphasizing the idea that even though you have the same number of particles of each of these different substances, the amount of space they take up is different, and the mass they have is different. We looked at problems that were comparing equal moles or different moles, equal grams or different grams, figuring out which has more mass, which has more moles. So we'll go through a couple of them now. So in this column, we're looking at samples that contain more mass, right? We want to pick out the one that has more mass. 1 mole of chlorine, Cl2. Remember, we write Cl2 like this because chlorine is diatomic. Or 1 mole of arsenic. And we have to look at the molar masses for each of them. So 1 mole of chlorine, again, its diatomic is Cl2. The periodic table tells me that monatomic chlorine has a molar mass of 35 grams per mole, but times 2 will be 71 grams per mole. Where the mass of 1 mole of arsenic, if we look at the periodic table, has a mass of approximately 75 grams per mole. So this mole has more mass in it, 75 grams versus 71. If I compare a mole of cobalt versus 2 moles of aluminum, cobalt has a molar mass of about 59 grams per mole, and aluminum has a molar mass of about 27 grams per mole. But we have 2 moles of aluminum, 27 times 2 is going to get you 54. This still has more mass, 54 compared to 59 grams. So what's interesting here is just because I have more particles of something doesn't necessarily mean I have more mass, because we have to take into account the mass of each individual particle. In the last example in this column, we have 4 moles of water. Water has a molar mass of 18 grams. And we're comparing it to 3 moles of CO2. CO2 has a molar mass of 44 grams per mole. So we have 4 moles of water, so that's 18 times 4, that would be 72 grams per mole. And then 44 times 3 would get us 132 grams per mole. So 3 moles of CO2 has more mass than 4 moles of water. Now in this column, we're looking at which contains more moles. Again, we have to use the molar mass. So we're looking at 300 grams of Cl2 or 300 grams of aluminum. So Cl2 has a molar mass of 71 grams per mole, and aluminum has a molar mass of 27 grams per mole. So which one has more molecules, or which one has more moles? Well, each mole of aluminum is only 27 grams. We can fit more moles in 300 grams of this than we can in 300 grams of this if we think about what the molar masses are, right? So 71 grams per mole versus 27 grams per mole. Now we looked at conversions, which we're going to practice in a minute. You can convert them, but you shouldn't have to here. Understanding I can fit more moles of this in 300 grams than I can fit, right? I'm going to reach 300 grams first if I keep doubling, tripling, quadrupling this than I will with 27 grams per mole. 100 grams of aluminum versus 200 grams of mercury. Again, aluminum is 27 grams per mole. Mercury's around 200 grams per mole. So there's just about 1 mole of mercury, where I obviously have more than 1 mole of aluminum, so there's more moles of aluminum here. We'll circle that one. Oops. Make sure you have the answer there. And then our last example is 300 grams of iron or 200 grams of chromium. So chromium has a molar mass of about 52 grams per mole, and iron has a molar mass of about 56 grams per mole. So even if we round this off to 50 just to make our life easier, right, just for estimating purposes, 200 grams of chromium would be about 4 moles if each mole is about 50 grams, 52 grams. 300 grams of iron, even if we estimated this molar mass to be about 50 grams per mole, that can go into here about 6 times. So that's about 6 moles of iron that exist in that sample. So there's more moles in 300 grams of iron than in 200 grams of chromium. The last thing we looked at was formally setting up mole conversions. So we're going to work through a couple of examples here. Remember that we have two conversion factors that will help us here. We have molar mass, units of grams per mole. So molar mass for a specific substance we can calculate using the periodic table. That will help me convert between grams and moles and grams. We also have Avogadro's number, the 6.02 times 10 to the 23rd. That will help me. That number is telling me how many particles are in a mole. So those are the two units that we can use to convert between, and this diagram helps to show that here, right? The mole is what links grams and particles. And here are the conversion factors that we can use to go between either of those units. So the first example here, how many molecules do 5 moles of water contain? So I need a conversion factor that brings me from moles to molecules. That's Avogadro's number. So we're starting with 5 moles of water. We know from Avogadro's number that each mole of water, and again I'm putting that in the denominator to cancel, contains 6.02 times 10 to the 23rd molecules of water. We plug that into the calculator. We're going to get 3.01 times 10 to the 24th water molecules. All right, the next example. How many grams does 2.5 moles of copper atoms weigh? So I want to go from moles of copper to grams. I can do that in one step by using the molar mass. Look at the periodic table. Copper has a molar mass of about 63.5 grams per mole. So each mole of copper is 63.5 grams. Moles will cancel. I'll be left with grams. If we do that, 63.5 times 2.5, we should get 158.75 grams of copper. The next one says how many moles of, and I'm going to change this because technically the particle that fluorine exists as are molecules. How many moles of molecules are there in 70 grams of fluorine gas? It's not asking for how many molecules individually, it's asking for how many moles of molecules. So I'm starting with 70 grams of fluorine gas. Now fluorine gas, remember, is one of the diatomic elements. And that's important to remember because that's going to change how we calculate the molar mass. If we look at the periodic table, fluorine has a molar mass of 19 grams per mole, but that's monatomic fluorine. If it's diatomic, we have to multiply it by 2. So it's 38 grams of F2 for every 1 mole. And if we calculate that, we get 1.8 moles of F2. And then the last example is how many molecules of carbon dioxide are present in 88 grams of carbon dioxide. So 88 grams of CO2, if I want to calculate individual molecules, I don't have a conversion factor that will bring me from grams to molecules right away. We have to make a pit stop at moles. I can use the molar mass to go from grams to moles, and then we can use Avogadro's number to go from moles to molecules. So the molar mass of CO2, if we calculate, it's 44 grams for every mole. And then I know in each mole of CO2, there's 6.02 times 10 to the 23rd molecules. Make sure the units we don't want cancel. We're left with molecules. And if we calculate that, we get 1.204 times 10 to the 24th molecules of CO2. So you should be familiar with how to do those simple mole conversions for this chapter, and that's where we left off with chapter 14.